first record the session, so that's done. Okay, so Giorgio Adamo received his first Master of Science degree in telecommunication engineering from the Polytechnic University of Milan, and his second Master in ITC from the Royal Institute of Technology of Stockholm in 2005. With the time TIAME. What does it mean exactly, Giorgio, this?
I think stands for Top Industrial Manager of Europe.
Okay.
Yeah.
Thank you. So it's a double degree program. Then he moved to the University of Southampton, where he obtained his PhD in 2011 and was awarded from the EPSRC postdoctoral prize for his study on free electron-driven nanoscale light source, considered to be the first step toward a chip-based free electron laser. So that's a very important topic. Then Giorgio joined NTU in 2012, where he was key in setting up and managing the Center for Destructive Photonic Technology, CDPT in short, and is currently a principal research fellow associated to this center. So in NTU, he broadened his research interest toward the physics and application of quantum and topological nanophotonics and pioneer studies on atom-photons interaction in nanostructure landscape, and introduced topological insulator and perovskite as a new material platform. Most recently, he extended his research to highly structured photonics and super resolution imaging. So that's fantastic. So thank you for being here again, Giorgio. So the floor is yours.
Okay, thank you, David, and thank you, everyone. So as I promised in the title of my talk, I will try to take you through a nanophotonic journey, which I hope all of you will find interesting. And let me start, even though, let me start, even though David already introduced myself. I will just go quickly through a graphical way. I mean, with many of you, probably we exchanged some chit chat. Some of you know me better, but not all of you know me. So I was born in Sicily, here in Italy, and then I moved for my master's in Milan. Then I joined this double degree program to do a second master at the Royal Institute of Technology. And then I moved for 2 years back in Milan to do industrial related research in the University Industrial Labs, where I basically started getting a flavor of research. I started liking research. So I decided to continue with a PhD, and I moved to the University of Southampton, where I got my PhD in physics and optoelectronics. And then through the prize, the fellowship, I managed to have an extra year as a research fellow there, where I could pursue my studies further. And then I moved to NTU in Singapore, where I helped setting up the Center for Disruptive Photonic Technologies, as probably many of you have seen by walking in the SPMS, and moved from senior to principal research fellow. So one theme that I try to find to connect all of this, besides science, is that I realized that somehow I cannot spend much time away from the sea. So all the places I come from, they're very readily accessible to the sea. So I lived in an island as many times as well, in most of them. Okay, so since this is an NAP related presentation, not just a research presentation, let me start you to giving you an idea of what my NAP, to setting up the scene, showing what the NAP proposal is about. So the NAP proposal was conceived by acknowledging the fact that in optical microscopy techniques, there exists an optical microscopy gap. So you have conventional microscopy technique on the far end that can go to the resolution of upper limit. Then you have high resolution optical technique or nanoscopy technique that can push down to about 30 nanometer. And then actually you have this microscopic gap or a valley because there is no optical microscopy technique there. And then you need to rely on electron microscopy technique, which are great, but they come with the disadvantages. I indicated here the resolution power. With the electron microscopy, you can go to the picometer, sub-nanometer regime, and what kind of objects roughly you can resolve with this resolution power. I will show that what I set to do for the NAP proposal is to tackle this optical microscopy gap and develop a microscopy technique that undergoes under the name I called super resolution topological microscopy, and I will spend a few slides at the end to give you more details about it. But first, the first thing I want to do is to basically show you the building blocks that across my career have helped to provide me with the tools to actually tackle the challenge of super resolution topological microscopy. I had quite few research interests, and I basically put them and collated them in three main topics. One is the development of coherent nanophotonics under the electron microscope. Of course, coherence, you know, it is important for imaging. And then another topic is the control of light-matter interaction by nanostructured optical fields. And the third one is the design of topological electromagnetic fields and how these are connected to the topological microscopy through these layers, which probably many of you already guessed. They are neural network layers, will be probably clear by the end of the presentation. So let me start by talking about coherent nanophotonics under the electron microscope. So the first question is why coherence and why coherent optical fields are important? Well, coherence is one key concept in optics and is strongly related to the ability of optical fields to generate interference. And this is the presence of interference or the lack of interference or the low or strong coherence is actually very important in a series of applications. There is many to list here. I just talked about that. I just mentioned lasing, in imaging, interferometry, metrology, and so on. So my research career started by addressing this topic. How can you generate a coherent light source? There is many coherent light sources. One special place is actually taken by electron beam driven light sources for mainly two reasons. They are extremely highly brilliant, they have a high brightness, but also they have a huge size. So they are usually building or much bigger than a building size. So we wanted to try to see if nanophotonic design strategies could be used to scale it down to a chip level. We named the type of source that we developed the light well, as you can see in the title, and also from the design, you can understand why. It is made by an alternating multi-layer of gold and silicon of about 200 nanometer each, and we go to a depth of about 2 to 2.5 micron. So we have a multi-layer, and then we milled with focused on beam milling, and the whole rate changes in the experiment. We changed the whole size. The one I'm going to show you is the one with the diameter of about 700 nanometers. So then what do? We just shine the electron beam through the hole and we detect the light that is emitted. How exactly we do? We employ a scanning electron microscope. Ideally, we would like to have a very highly collimated electron beam, but electron microscope gives you enough depth of focus and collimation, about a few microns, so it's enough to characterize the well. What do? We shine the electron source, and then the electron source goes through a parabolic mirror, through a hole, goes through the well generates light, it's collected by a parabolic mirror and sent to a spectrometer, and then finally the spectrum is detected by a CCD array. There's a technique that is called catoluminescence spectroscopy. What we did was to raster scan the electron beam across the light well so that we could see the emission regime depending on where you are illuminating the well. And we identify mainly three emission areas. So the center of the well, or around the center of the well, where you have low emission. You should have ideally no emission. You have a little bit of emission coming also from probably the material that is left at the bottom of the well. Then you have another area of emission, which is around the well and is also very far away from the well. As you can see, there is no change when you modulate electron energy. The peaks stay at the same position. And this is basically luminescence from the material components, gold and glass. And finally, when you approach the well, you observe that clear peak appear in emission, and they actually change spectral position when you modify the electron acceleration voltage. They blue shift when you increase, they red shift when you decrease. So this is all in line with the idea of the emission mechanism. Compared to a proper free electron laser, the emission mechanism we had in mind is called Smith-Purcell radiation, where you have a free electron that travels on top of a grating, and the modulation of the dielectric environment that is felt by the electron beam allows the radiation to be emitted. And you have a proper correspondence between speed and wavelength of emission and angle of emission. We further characterize the weld. We increase the intensity to see what kind of emission regime we are. It looks like we're still in the linear regime up to the beam current of a few nanoampere. We also see how the emission evolves while you approach the well from the center to the distance. And you can see that from a zero or flat emission, when you're close to the center, you start feeling the dielectric environment when you approach about 150 to 100 nanometer away from the well. And the emission mechanism itself, as I described before, is related to the Smith-Purcell, but is not purely a Smith-Purcell emission. Actually, the well is a 1D photonic cavity. So you can generate the photonic modes supported by the well. This is a very simple description. It's a theoretical description of the well. So it's a modulated gold well rather than a multi-layer, which becomes much more complex. But nonetheless, when you, you plot the light line and the lines, the light line like for the speed of the electron, you see that the experimental points, they fall very close to the intersection between the electron energy lines and the modes of the structure. So beside this first example, we started being more interested. We said, okay, we can generate something that looks like it might become coherent. Can we find other strategies, other mechanisms to engage coherence? Can we have a material, devise a material where you have a local excitation, you start have the material oscillating with a superposition of modes. Can you filter the superposition of modes so that you have a collective response from them, which in turn will generate a coherent light emission? So the question is, can we have such type of material? The first material we looked at, and quite successfully, is what is called coherent metamaterial. Coherent metamaterial are a special kind of nanostructured materials where the spectral response is not dictated by the single resonance of the single element, the single atom of the material, but from the ensemble of it. As you can see here on the bottom, for an incoherent metamaterial, you have the same quality factor of the resonance, independently of the number of unit cells that you're illuminating. This is through far field illumination with a plane wave. While if you do the same thing with a coherent metamaterial, the quality factor becomes better and better. And this is because the mode supported by the coherent metamaterial is actually a magnetic dipole that is perpendicular to the surface of the material. Therefore, the emission happens on the surface. It cannot easily decouple out, and you engage a collective mode out of it. So the real question is, can you actually generate such a mode? Can you engage such a mode by actually exciting the structure on a single position? It looks like you can. So we did the theoretical estimate. We described the metamaterial as a set of dipole that are oscillating in antiphase, one against the other one, and we drive it through the center. And you can see that there is three main modes supported by the structure. But the one that has a higher strength is this M11 mode, which actually is phase meshed to a plane wave that is incident perpendicular to the array. So the excitation of this mode locally from the center can generate an electromagnetic wave with a uniform phase front that propagates away from the array. In order to test this experimentally, what we did, we created an array about 30 by 30 micron with a unit cell of 220 nanometer, where we have this asymmetric split ring. And then we illuminate with the electron beam, and we approach the center of the array in step by step. And you can see here from the picture that the emission changes the more we approach. When we analyze, we see that while we come with the injection point closer and closer to the metamaterial, when we start engaging about more than 5, say, units, you start seeing emission. The emission picks up until it saturates, and at the same time, you see a line with narrowing, which is a sign of a temporal coherence being built. We also tested the sample for spatial coherence. So we did the same experiment, but this time, instead of looking at the spectrum, we filter at the main peak of emission, and then we take an image directly on the CCD. When we look at the image of the emission of the metamaterial array itself, you can see that it's mainly collimated around the center. The divergence is not very small, but it's not very high. It's about 30 to 40 degrees. So this means that the material is starting to build spatial coherence in its emission. So now let me move to what the research that then I started doing when I came to NTU, which is applying the same or a similar nanostructuring criteria to control light matter interaction. Because when you will do microscopy, you will definitely have light matter interaction at the nanoscale. So there is different ways you can engage light matter interaction. In the works that I did in NTU, I was involved in a few of them. I was involved in the tuning of the Casimir-Polder interaction in a material system that is composed by a metasurface, a plasmonic metasurface, on top of which there is a free electron gas running across, where we actually can tune by changing the resonances of the metamaterial, the interaction between the two material systems. I did some works where I looked at the enhancement, the Purcell enhancement in light emitting metasurfaces, in this case also a hybrid system or all dielectric system, the enhancement of optical activity and through design of superstructural chirality. There is also other things, of course, you can do through light matter interaction. You can enhance nonlinearities, you can control quantum emission and absorption and so on. But what I want to focus in particular in this case is the first demonstration that I'm aware of, where you can use nanophotonic structuring to control the topological electronic transport of topological insulator materials. And this is the topic I selected to dwell on. So let me quickly introduce what is a topology insulator. We use a 3D electronic topology insulators, where you have a gap bulk insulators that is coming with Dirac type surface dispersion bands. And since the surface bands have Dirac dispersion, then this comes with the physics of relativistic Dirac fermions. The surface states are topologically protected by time reversal symmetry, which means that the charges can move by being very small affected by scattering. A last parameter that is interesting in the experiments I will show is that the spin of the surface carriers is locked to the momentum. So you have spin momentum locking on the surface. How do you describe the topology insulator from the photonic perspective, the way we started describing? You can imagine having a dielectric bulk where you with high refractive index, which is enwrapped by a metallic surface that has more plasmonic behavior. So the fact that they are inherently connected allows you to think of possible ways to generate high, strongly resonant structures designed by using the high refractive index of the bulk to engage the surface states. You could think about having plasmons that have long propagation, or you can have engaged the spin momentum locking of the carriers to control them by controlling the polarization of your light. So with the material structure, the material platform that we use, this BSTS, is bismuth, antimony, tellurium, selenide. And by doing first principle derivation DFT calculation, we observed that when you calculate it in a slab, you observe the bulk, you observe the band inversion, and the appearance of the Dirac dispersion bands at the K point, the gamma point. So one other thing that the DFT calculations show that is quite interesting is that when you turn on the spin momentum, the spin orbit coupling, you actually see that the surface charge state starts accumulating, which is a clear sign that you have surface states building. But our experiments are made by a crystal that is exfoliated and is done at room temperature. So we were worried whether the surface states were actually surviving in the samples that we are using. So we engaged some collaborators in Milan that have time-resolved ARPES, and indeed this shows that BSTS surface states do survive at room temperature. You can see the creation of the surface states that are very clearly defined. we started with the nanostructuring schemes, and we observed that, for example, you can create UV and visible plasmonic resonances in the BSTS, and you can actually image by nanoscopy technique like this NOM, the modes that are supported by the structure, either on artificially created, for example, discs made with the focused ion beam, or in natural flake exfoliated and become very small in size, as you can see here in the picture. We also saw that you can actually follow the resonances all the way from the visible to the infrared up to almost 10 micron by changing the slit length. And this supports a quite strong modulation, given by the fact that in the infrared, especially, you have a quite high refractive index. What we expected to be just a simple dipolar resonance actually resulted to be a very complex nature of the resonance. You have multiples, many orders multiples that are engaged in the resonance. And what we observed from simulation, of course, is that the resonant fields have the circulating currents on the surface that appear. This could potentially be employed to couple with the spin polarized carriers that I mentioned just before. However, all the examples I showed up to now basically fail in showing that you can engage solely the surface of the topology insulator. So we decided to change a little bit perspective, and we relied on the fact that topological insulator carrier, they have a very unique dependence on the light helicity when you illuminate. So they can selectively be excited by circularly polarized light. When you come at oblique incidence, if you come at normal incidence, you will not be able to excite selectively surface carrier with a specific spin. But if you come with oblique incidence, you will be able to selectively excite carriers with a specific spin, and therefore you will be observing topological transport. So when you do this experiment, you will observe a curve that looks roughly like this. So the current is a bit more rich than just circular, the response to the circular polarization. You have mostly 4 components, 2 of which are actually surface terms and 2 of which are bulk terms. You have a 2D periodicity you can identify that goes as a 2 phi when you rotate the polarization of the polarization axis, and you change from linear to right circular to linear to left circular polarized light. And then you have other periodicity dependence, which is a 4 phi, and one that is independent of phi, which is a bulk contribution, thermoelectric contribution. What we want to focus on is specifically the 2 phi periodicity here. So our working hypothesis was, if we nanostructure now the material, first of all, will the surface state survive? Second, will the absorption that is dictated by the metamaterials, as you can see here, by the metamaterial design, we can obtain an increase, like a doubling of the absorption, have an effect into selectively exciting and selectively absorbing spin carrier with that are sensitive to the circular polarization of the light. So we decided to start with a metamaterial that does not have any effect on optical photonic chirality effect, because we want to start observing something that reacts properly the same way to left and right circular polarized light. And we did the experiment on a structured BSTS flake first, and then we follow on the same flake with nanostructure the BSTS with a metamaterial that is made of rings, square rings. And what you observe on the unstructured flake is a typical modulation like the curve you saw before. And presence of this circular photogalvanic effect, this 2 phi component, can be seen by the modulation of the peaks that appear either at one or the other circular polarization. When you do the same experiment on the structured metamaterial, you observe a completely different behavior. You observe basically a modulation that is dominated by the 2 phi components. If you extract the coefficients of the formula that I showed before, you see that actually the dominating part is mostly circular photogalvanic effect. So by changing by modifying the imbalance between the surface state at with the opposite helicity, you can actually increase this modulation. What I would like you to notice here is that what you observe here, you should consider as a modulation that is stretched both in the vertical and opposite direction. So the material reacts at the same way whether you go with a right or a left circular polarized light, and generates the same amount of current. So the following step was naturally to try to introduce some optical chirality. So we structured the metamaterial with two metamaterials with opposite twist, one left twist and one right twist, which when you come at 45 degrees incidence, at oblique incidence in general, in this case is 45, they show a very clear circular dichroism, which is mirror symmetric for the two kinds of metamaterials. And what we observe now is a very different picture. You see that in the structure pattern, we try to reduce now the effect of the thermoelectric contribution. So we try to set the photocurrent almost around zero. You see a small wiggling. But now when you come with either on the right twist metamaterial or on the left twist metamaterial, you see a reversal of the effect. And this becomes more clear when you actually take a ratio between the two. So first of all, we observe a much higher increase of the CPG. We go this time from between 50 and 100. And what we observe then is that actually you can kind of suppress by a twofold well, let me call it the unwanted chirality in the sample. So effectively, you identified a way to control the topological response, electronic topological response in the material. Then, after having this nice realization for the topology design for in the near field, we started asking ourselves, is it possible to think about a design where you now generate topological features in the far field? I've been doing a few examples on how you can control far field by nanofield structuring. So I've been involved in the demonstration of super oscillation. You will see why they are important in a while. I show polarization control, optical field routing, and you can do many more things. You can do laser emission, optical angular momentum control, and so on. So the question was, now, can you actually generate this topological features in the far field by acting directly on the source of the emission light or the emitted light? In order to demonstrate this, we decided to work on a perovskite platform. We decided to work on it because of some unique features. It has a relatively high refractive index. It emits quite well, and it can be tuned. And you will see that all this will come handy in the demonstration that I show in the next few slides. And the optical design we decided to engage this time is a bound state in the continuum. And the reason is that bound state in the continuums are very high. They are very almost theoretically infinite Q factor resonances that are actually happening in the continuum, the bound state that appears in the continuum one. And when you have an emission, for example, they will appear as intensity minima at the center of polarization vortex laser beams. And if you follow the polarization across the vortex and count how many times the polarization winds while you complete a full circle around the polarization, you can determine the topological winding number of your polarization. That is supposed to be an integer. The design we use is, it has an in-plane inversion symmetry design. And we realized it by nanoimprint lithography on a perovskite film of about 250 nanometer thick, which is embedded into two 1.5 refractive index platform. So when we excite with 405 nanometer laser light in the blue, we observe laser emission. And as you will see, this laser emission will have a clear topological winding number of 1. Another interesting thing is that the perovskite can actually undergo phase transition. So once you modulate the phase transition of the perovskite, you will be able to see that the metasurface, which supports more than one mode, will start emitting laser light with the polarization vortex that has a winding number, a topological charge of -1. We started doing experimental simulations to design the structure, and we designed a structure that has got two resonances, a magnetic quadrupole and a magnetic dipole, BIC. And as you can see, they lay very close to each other. By changing the temperature, which will induce also a change in the refractive index, you will see that the modes of the structure will shift in wavelength. And here on the bottom, you can see the modes of the structure in the near field and also the polarization associated, where you can see there's a topological charge of +1 for the magnetic dipole and -1 for the magnetic quadrupole. The realized structure in with the nano-imprint lithography is shown here. You can see that is a very nice flat surface. And indeed, the experimental PL maps show both emission in both TE and TM, where you can identify the two BIC modes in emission. You can see there is a clear black point appearing, vanishing intensity here. Then we pumped the metasurface with a laser, as I said, with a femtosecond laser to test the lasing capability of the metasurface. And indeed, we observed a lasing light line with a typical S shape. And in the first case, at room temperature, we observed emission with laser emission with a threshold about 8 microjoule per centimeter squared, and the collapse of the line width. At lower temperature, we see that there is again only one single lasing mode. Now the threshold is lower, it's almost 1 order of magnitude lower, it's about 8 times lower. And the line width also collapses there. So the line width is almost sub-nanometer. So we know we're in the lasing regime. When we do imaging, real space imaging of the device, of the emitted light, we observe a typical donut shape, so the typical vortex shape that we expect. And then we follow the winding of the polarization by rotating a polarizer in front of the camera. And you can see that for the mode that is a dielectric dipole, magnetic dipole, you can see that the winding number is +1. And for the magnetic quadrupole, you can see that the winding is in the opposite direction, giving a topological charge of -1. If we follow the emission through the whole cycle of temperature, so simulations show that both modes actually shift. But thanks to the gain loss overlap, what we actually observe is in the lasing regime, while in the PL, you will observe both of the modes. In the lasing regime, you see one mode when you start cooling the structure that continues to persist even when you go in the transition region, and then it switches to the other mode, to the magnetic quadrupole BIC. Then it stays until you continue to cool, and when you go back, you show retentivity. So in the end, you create a dynamic switch between one and the other one. And you can have a single temperature where you can actually switch dynamically between one emission and the other emission, with the emission with one polarization vortex singularity to the emission with the opposite polarization vortex singularity. We continue to investigate the ability of BIC to control the polarization, the polarization distribution in the far field by now breaking the in-plane inversion symmetry. So if you break the plane inversion symmetry, the integer charges that are associated with BIC, they will break into 2 half-integer charges, each of them associated with a perfect circularly polarized emitted light. And in order to see how the polarization spans the entire Poincare sphere, we take a back focal plane imaging. We do also simulations to see what kind of polarization you would expect. And you see that actually you will see a 4-lobed intensity in the simulation, which is shown very well also in experiment. And on half of the hemisphere on the left, you will see mainly a right polarization. And on the other half, on the right half of the polarization or the hemisphere, you will see mostly a left-handed emitted light. If you do, if you measure the degree of optical polarization, you actually experimentally, or theoretically, you can obtain a fully polarized, circularly polarized light. Experimentally, we obtain up to 0.6 actually for a small change in the design. So it's an extremely high degree of circular polarization in the light that we emit. So now all these building blocks will come into the help to rescue, to build nanophotonic strategies to create microscopy that goes much beyond the diffraction limit. So let me take it back to the slide that you saw before, and let me get rid of the conventional microscopy. So let's focus more on what we call nanoscopy techniques. You have Stead, Storm, and Palm, which are very interesting, but suffer from the fact that you need to have labeling agents, fluorescence emitters. So in this case, sometimes this is unwanted, sometimes it's not possible. Similarly, for SNOM, you need to be in contact with the sample. Besides, you can see that actually the resolution of the picture of the virus you saw before, when you go for a resolution of 30 nanometer, you will not be able to resolve all the parts to the resolution that you want. So how can we cover this space? So we need to find a way to break with the conventional schemes. And the technique I'm going to suggest will be able possibly also to enter and explore space, because the resolution that it promises, it can go to lambda over 1,000. So in this case, you start entering a regime where, for example, you will be able to see a Brownian motion of your nanoscale objects. What kind of technique are we going to employ for this? So what we need is a highly structured field in the far field that have got singularities that change much faster than the wavelength of light. So one way of doing it is a famous way of doing it is to use super-oscillation. Super-oscillations are built on the idea that functions that oscillate, once you sum them up, can oscillate much faster than the highest Fourier components that constitutes them. And this is shown on the schematic here on the right. You can see that the oscillation in one specific point in space happens much faster than the highest Fourier components, which is shown by the dash curve here. How do you generate these super oscillatory features? Well, you can use a nanostructured phase or intensity mask. In this case, a silicon phase mask that you see here. And typically you will see a hot spot appearing in the far field. The hot spot is sub-wavelength, it breaks the AB-Rayleigh limit, and has been used to show imaging that go almost to lambda over 8, lambda over 10, also the real live in vivo imaging of real cells, neurons in that case. But one thing that wasn't realized till recently is that beside the center hotspot, this field carry gigantic wave vectors that are highly localized in zone that go experimentally to lambda over 400. And they've been used even more recently to show experimental resolving power, in this case was a metrology, but of a lambda over 400, which can theoretically reach lambda over 4,000. So another component I want to use in building this technique is using the power of artificial intelligence for sub-wavelength imaging. So very recently, we developed a technique where we decided to image very simple objects. So to start with a very simple geometrical object, 1D, a nanoslit of a varying size, and we illuminate with plane wave illumination. We collect the scattering pattern, we move the position of the slit so we can collect at different height and different position, and we create enough scattering events to be able to feed to an artificial neural network. After the artificial neural network has been trained enough, you can feed scattering pattern from slits that the neural network has not seen before. And we demonstrated that even with using plane wave illumination, you can retrieve parameters of the slit. This is not imaging yet, but you can retrieve parameters of the slit that with an accuracy that surpasses lambda over 200. So now what we would like to do, and what I would like to do for my MEP, is to engage optical topological singularities in the process. So the full scheme that you can see there here describes the full experimental idea. You start with a topologically structured light. How do you generate? You start interfering coherent wave, like a laser light, with a metasurface or with a spatial light modulator, or you might think of generating directly in the near field with a source that is structured to generate topologically structured light in the far field. And then you illuminate an object, you change the position either of the object or the field, and you generate a certain number of scattering events. What you need to know is that actually inverse scattering problem is a nilpoise problem, which is treatable by integral equation, which are ideally suited to be solved by neural networks. So once you generate enough training data, you can feed to the artificial neural network. Ideally, would be very, very nice to develop a virtual twin microscope. Would be ideal to develop a virtual twin microscope where you can generate scattering patterns that can substitute the experimentally generated one, or at least partially substitute, because you will reduce the experimental load needed. So once you once you feed to a diffusion network either experimental scattering pattern or a virtual scattering pattern, then you might be able to train it to the point that when you feed now an unknown object with an unknown shape, it will be able to reconstruct the shape with an accuracy that is of the same order as the singularity you have been illuminating the object with. So lambda over 1,000, it's achievable. So once you get there, so here I list a few possibilities, but once you get to a resolution of lambda over 1,000, you can gauge the impact that this can have on a set and a series of areas and the microscopy modalities. So let me close with the picture that I showed before. I hope that through this quick journey through nanophotonic, through nanophotonics under the microscope, through coherence and the control of light-matter interaction and the design of the optical fields, both in the near fields and in the far fields, and with the help of the neural networks, this will help me tackle the super resolution microscopy that I mentioned before. So let me close. I think I should be in time. There's too many people to thank. So I put the list of people that have been involved in the papers that I specifically dwelled in. There is many others that have been involved in the other papers where I glanced, but they didn't fit here. So let me close here. I think I'm just in time, David. So thank you very much, everyone, for listening.
Yep. I think you're perfectly in time, yes. Thank you, Giorgio, for this very nice talk. Session is open for questions. So, Giorgio, let me start eventually. I mean, so that's a very exciting perspective for this, super resolution imaging. I mean, okay, the example you show, is the plane wave and the slit. I mean, I was thinking to myself, okay, at the end is also a question of signal to noise ratio, but also somehow, I mean, if you want to obtain this kind of super resolution, you need also to control very well the wave in which you excite your sample.
Yes.
I mean, is it really something that can be is it manageable or? I mean... Well,
I mean, so we. I started working a little bit on this. It's challenging, but it is possible. Of course, you need to, you start fighting against much more than a normal microscopy, against vibrations, against environment, against drift with respect to each other. So you need to manage all of them. So you need to think about stability a lot, but it seems to be manageable. We start having some evidence that it's manageable, right? You have, I've seen some experiments where you can go down to, well, very, very, not as far as lambda over 1,000, but very close to it. So it is manageable. You have seen, for example, in the science paper that is a metrology experiment, but they managed to do metrology with the lambda over 400. So yeah. And then the idea would be, of course, the more you integrate, the less it will shake, but that's too far the line, right? Starting, you need to fight environment. Yes, you cannot pretend it's not there.
Okay, thank you.
Yeah.
Yes, Jesus, you want to say something?
Yeah, very nice talk.
Thank you.
Yeah, very nice talk. I was wondering, in your last part, so you have shown that you want to use singularities to enhance the resolution and to train your network.
Yes.
I was wondering, so you have shown just first order singularity, so with topological charges +1 or -1. I'm just curious, do you have any hint that the resolution will depend on the order of your topological singularity? I mean, is it if you use +2 or -2 or higher order, do you think, or have you made any calculation on the effect of the topological order?
So we haven't done yet. So this is all open to research. So actually, at the moment, the singularities, we use it only as a very sub-wavelength needle, you can call, right? But once you start engaging, for example, with materials that are sensitive to the topology of the field you are illuminating with, I don't know, 2D materials or quantum materials, then you might see different effects by changing the order of the singularity, but we haven't gone as far. So this is just an outlook of a very long research team that is just started.
Thank you.
Yeah.
Thank you, Jesus. Other question for Giorgio?
Giorgio, I have a question.
Yes, yes, hi.
So because you talk about several areas which made a significant contribution. So, if like I'm trying to combine all of them, so eventually the outcome could be you use the TMD or perovskite materials which is topologically protected, and the electrically powered, you have this very, very nice, very small light source or laser could be, and you combine with your super resolution microscopy, and you will produce something very small and which might have a like lambda over 1000 spatial resolution, which will allow you to see the chemical bond in the kind of atoms. Would that be the one of the ideal outcomes?
Yes, yes. So actually, one of the idea that I flagged in the proposal is the possibility of integrating all of it. So you might be using some of the design principle plus some of the, for example, the emission, like you saw the perovskite or electrically driven them. Or it doesn't have to be perovskite. It can be any other material that has a similar property that can emit and be structured on the nanoscale, and you can maybe electrically driven it. And there is a lot of room to play with. So I think if you were able to generate a microscope that is so integrated that you can bring it with you, even lambda over 100 already would be fantastic, right? Imagine you can just bring it as on your box, and then you can have lambda over 1000, and that would be
that will be really, really exciting.
Yeah. Yes.
Okay. Thank you.
Giorgio, can I ask
yes.
here? Can I ask a very question, maybe not too much relevant, about the perovskite thin film laser, this polarization result laser? What kind of perovskite is a very thin film or mono layer? Or
no, this is a standard. There is a MAPI. There's just a 3D perovskite. Yes, it's still
solution
a 3D
processed.
perovskite. Yes. Solution processed. Yes, yes. So the idea was just to use something that is solution process, so we can do nano-imprint lithography for the quality. If you use a crystal, maybe you need to do other structuring technique. There may be beam lithography and so on, but this is just solution process to start. But if you use 2D, it's also very interesting. Actually, you might have effects that are not present in the 3D one. And you could go even thinner. It depends also on the refractive index. So you cannot go too thin and have the same design, because then you will not support the structure, but you might think of encapsulating in other designs.
Yeah, but is the perovskite solution process of thin film quality, is it good enough for?
Yeah, it is very good actually. So it is good, and actually you can see that when you do nano-imprint lithography, we observe that the quality of the perovskite becomes even better, because probably when it's under, so it's put under very high pressure and temperature processing of the nano-imprint lithography, even the surface morphology becomes better, environmental stability becomes better, and even lasing becomes better.
Okay.
Yeah.
Thank you.
You're welcome.
Giorgio, I have a question.
Yes, I would.
So in your super resolution, you are depending on this interference of this wave front, right? You make some metasurface. So how about the polarization phase? Will this one change or not?
So you can design actually. So you can design other metasurface that where you can control the polarization almost on every point of the diffracted pattern. or you can use a specialized modulator where you can get a very complex design where you have phase singularity almost wherever you want in space.
For the normal one, the one you used, will the polarization change or not?
The polarization, I think you can. So we did, for example, in this case, you can, it's a metasurface that will have a different response depending on the polarization. So you use actually, for this experiment, they use all the 4 polarization to retrieve the images. So each polarization carries a different information. So it depends on the design. So you, for example, this one, you can illuminate with linear polarization, or you can think of illuminating with the radial polarization. Every time you can adjust the design depending on the polarization you want to use. So it's a very well, open toolbox to play with, I would say.
Okay, thanks.
Yeah. Well.
Okay, other questions in the audience?
Giorgio, can I ask another question?
Sure.
Not scientific, because this is because this talk is related to application for NLP. So I want to ask, do you also involve some teaching rather than just tutorials?
Sorry?
Did you involve some teachings in the?
Yeah. Well, I've been involved not in teaching per se, but I taught a lot of people. For example, I've been teaching a lot of undergrads and postgrads that joined CDPT how to develop nanophotonics, for example, fabrication techniques, or how to develop simulations. So I've been not doing like structured teaching like the university, like with courses, but I've been doing teaching quite a lot, I have to say. I trained more than 40 people, so I would call quite an extensive teaching.
Right, okay.
Yeah.
Okay. Still have a few minutes for very last question. No, so if not, thank you very much, Giorgio.
Thank
you,
the
best.
Thank you, David. Thank you.
See you around. Bye-bye.
See you around. Have a good day. Bye-bye.
You too. Bye-bye.